Well, good evening, everyone. It's truly a pleasure to speak to you today, such a youthful audience. And today, I'm going to be telling you about why I regard telescopes as being time machines. So, as Carolyn said, I'm a second-year PhD student here in the department studying cosmology, which is the branch of physics that studies the origin, evolution, and future of the universe. And in order to do this, we use big telescopes. That's me in the Canary Islands with the GTC, one of the largest telescopes in the world. And this here is the Future Simons Observatory, which is a telescope studying the relic radiation from the Big Bang, some of the oldest light we can observe. And this is a collaboration that I'm a part of. It's a really large international collaboration. And so one of the questions that I want to address today is why it is that scientists have to build such big telescopes and why we do it. So I will try to convince you that the reason we do it is because they're actually time machines that let us look back in time, and that when we do that, we discover that very early on the universe was basically just a soup with tiny lumps on it. And it is actually from those lumps that everything we know and everything we don't know evolved. Okay? But in order to understand these points, we need to first understand a more basic concept very well. And it is what we mean when we say that we see something. Okay? So, when we see an object, what's actually happening, for example, this blackboard, right? We see it because light is bouncing off of it and making its way to our eyes. And the crucial point here is that light actually travels at a certain speed. It's a very high speed. This is a huge number, much faster than your parents' car, for example. Right? But it's a fixed speed nonetheless. And even if in our daily experience, it seems to us that we see things instantaneously. When we see something, we're seeing it as it is right now. That's only because the distances in our daily experience are very short, and light doesn't have any trouble covering them very fast. And to us, this seems to be an instantaneous thing, right? But when the distances at hand are larger, such as, for example, the distance to the sun, things change a lot. So when you go out during the day and look at the sun, well, don't just look at the sun. You get what I mean? When you look at the sun, the light that you're receiving actually left the surface of the sun way before, well, not way before that, but sometime before that. Does anybody have a guess of how long it takes? Oh, so many hands. Yeah, so how long does it take for light to travel from the sun to us? So here in the first row.
About 8 minutes.
Wow, that's precise answer, very good. It's a little bit about over 8 minutes. Yeah, so actually we're seeing the sun as it was 8 minutes before the time that we looked at the telescope, right? And what this means is that, the sun could actually just, suddenly, imagine it turned off. We wouldn't notice until 8 minutes later. It's a bit scary, right? But don't worry, that's not going to happen for several billion years. Okay? So we can use the speed of light to define a distance. Much like when we talk of a mile or a kilometer, we can speak of a light year, which is the distance that light can cover in a year. And this will be very useful when we talk about things out there in space, because the distances are much larger. For example, the nearest stars are around 10 light years away. Right? So let me propose a bit of a silly example to understand what we just talked about. Suppose that around a star that's precisely 10 light years away, there orbits a planet, and that this alien lives on that planet. Okay? This alien likes to sit in this planet and read the daily newspaper. Okay? So suppose that after this talk, you might go out there and look through a telescope, and maybe you could point it at this specific planet and see the scenes that are going on in the surface of the planet, right? So you see the alien reading the newspaper. But if today is February 20th, 2019. What would the date on that newspaper say? Does anybody have an idea? Yes, what do you think?
Would it be the 20th of February 2009?
Precisely. Good job. Very good job. And that's around the time when Barack Obama became president of the United States. Sadly, we can't travel back in time. We can look back. But this still doesn't explain why we build bigger and bigger telescopes. And I think you'll understand this very easily. But objects that are further away appear fainter to us. And the reason is that the light they emitted, or the light that bounced off them, has had to spread over a larger area. Right? It's much like when you drop a stone into a pond and it generates ripples. And those ripples actually seem to die away, the further they get from the point where you drop the stone. It's because they've had to spread that energy over a larger area. So what we do is, when we build bigger telescopes, is actually just increase the area of this telescope. Like the larger the mirror, the more, or the lens, like the more light that we're able to collect. Therefore, we can actually see fainter objects. And what if we look at even larger distances? So take this, for example. So you might know that we live in a planet that's orbiting around the sun, and this sun lives in a galaxy. Well, there are actually lots of galaxies in the universe, trillions, okay? But they prefer to live close to other galaxies. So this is a cluster of galaxies, everything that you see here. Every dot is a galaxy, okay? And ours is around here. And I'm suggesting that we think of another galaxy far away that lives here, okay? This one. It's 60 million light years away. This is what it looks like when you point your telescope at it today. But actually, the light that you see left the surface of that galaxy 60 million years ago. That's around the time when dinosaurs were still on the surface of the Earth. But light has taken so long to get to us that plenty of things have happened on Earth. Dinosaurs went extinct, we developed as a species, and developed also the curiosity to look through telescopes and capture this light. Okay, so I think by now you probably understand the idea that the light that we see when we look through a telescope comes from the past, okay? So what happens when we look really deep into objects that are really far away? We're seeing scenes that happened a long time ago, right? So just how far can we look? Let's go on a little tour of the universe to look at objects very far away. We can start in our home, the Earth, with the moon orbiting around it. If the Earth is our home, then perhaps we can say that the solar system is our street. And our street is just part of a neighborhood. In this case, the stars that live around the sun, or near the sun. The alien that we spoke about earlier would live around one of these stars. And again, we can continue to zoom out and go to what would be the equivalent of our town, you could say. This is the Milky Way galaxy, our galaxy. This is what it would look like if you could fly out of it and look at it from above, okay? But you can actually see it in the night sky if it's a clear night. It's a really large galaxy. It has somewhere between 100 and 400 billion stars and more than 100 billion planets. And this is where we live, just in one of its spiral arms. As I said earlier, this is what it might look like. Has anybody here seen the Milky Way on a clear night? Yeah, it's a really cool thing to see. So if you can go to a place that's very dark at night, you will see a band of stars crossing the scene. And why does it look like this? Well, you saw here that the Milky Way is a spiral. It's like a disk, and we're sitting within it. So when we're looking towards the center, we're seeing the disk, right? If you look at the central bulge where lots of stars live, you see more stars. If you look towards the edges, you see less stars. And we really live in an amazing era where we can build really advanced telescopes that can measure the stars in our galaxy with great precision. So this here is a very recent image from the Gaia probe. It's a satellite telescope built by the European Space Agency and led by some people in this department, actually. And this satellite has measured the positions of many, many, many stars, millions of stars, in 3 dimensions in our galaxy, contributing to a very advanced understanding of its presence and of its origin. And this is where, this picture, this understanding of our galaxy is based on very precise measurements. And you can compare that to how scientists thought the Milky Way looked in 1885. That's really not that long ago. But I'm not trying to embarrass William Herschel here, actually. I'm trying to praise his work, because this was the first quantitative effort that anybody made to draw a map of the galaxy based on actual observations. But you can see how far we've gone, right? Not only that, like only 100 years ago, which is very recent in the grand scheme of things, scientists thought that the Milky Way was all there was to the universe, that nothing existed outside of our galaxy. But soon in the 1920s, people started discovering other galaxies around us, and unveiling a very different picture of the universe. This is our local group of galaxies. It's the Milky Way and 53 others, most of them smaller ones, dwarf galaxies, some of them pretty large. This is the Andromeda galaxy, and it's so big that you can see it with the naked eye on a clear night. But just so you get an idea of the scale of this little galaxy here, the Large Magellanic Cloud, it's actually very close by. But the light we see when we look through a telescope was emitted 160,000 years ago. Does anybody know what was happening on Earth then? I had to look it up, so I don't expect it. Oh, we have a hand. Yes?
Humans were evolved.
Exactly. Very good. So yes, our ancestors, the first Homo sapiens, were actually leaving the African continent to move to other parts of the planet. So that's quite a long time ago, right? But perhaps, from these measurements, I think the most remarkable thing that came out, and what I personally think is perhaps the greatest scientific discovery of the 20th century, was that all these galaxies, all the galaxies that we can measure, are actually getting further away from us. This was measured by Edwin Hubble in 1929. And he also measured that the further the galaxy is, the faster that it is fleeing, that it seems to be getting away from us. Okay? This is amazing, and it suggests the mind-boggling possibility that the universe is expanding. And because I know this is a difficult concept, I put together another silly example. But you can tell me if this analogy works or not. But I like to think of the universe as an infinitely big piece of dough that you put raisins in, okay? And each raisin is a galaxy. And the dough between raisins is the space between galaxies, right? And as you place this piece of dough in the oven, it begins to rise, right? Consequently, the distance between the raisins increases. And, 2 raisins that are close by only have so much dough in between. So, if a particle of dough expands, then the effect is relatively small. But if you have a lot of dough in between, and all of that dough is expanding, then this raisin seems to be getting farther from us here than that one. But of course, there's nothing special about this particular raisin, this particular location in the universe. The same should be true for any other galaxy in the universe or any other raisin in this bread. There's obviously a limitation to this analogy in that, in the case of the bread, the bread is actually expanding into the empty space around it in the oven. In the universe, this is not the case. By definition, the universe contains everything, right? But you don't actually need it to expand into anything, because it's actually the space between things that's getting bigger. In this case, because the dough is getting larger, and the dough is what defines the space, the separation between the raisins, the piece of bread seems to be expanding. So similarly, it's the space itself that's stretching in the universe. We're not expanding into anything. But another remarkable thing is that if the universe is expanding today, and we measure how fast it's expanding, you can actually play that back and calculate how long ago all of these raisins were together in the same place, right? And you can, in that way, measure the age of the universe. Does anybody have an idea of what that age would be? Yes, what do you think?
13 billion years?
Yeah, that's great. Good job. We have so much knowledge in the audience today. Yeah, that's precisely it. It's a huge number, okay? And I'm not sure that will mean anything to anybody, but if you basically take all of the history of the universe and you compress it into one calendar year, with the Big Bang in the first second of January 1st, and this moment as the last second on December 31st, then all of human history happens after 10:30 p.m. on December 31st. So a lot of history without us playing a part of it. All right, so we now know that telescopes let us look back in time. We also know that there is a beginning to the universe. So in principle, we could use our telescopes to look deeper and deeper into the universe, looking at earlier and earlier scenes, and potentially look all the way to the beginning, right? So let's continue our journey and see what's on larger scales from the ones that we're used to. All right, so from the local group, we've zoomed out to our cluster of galaxies, right? But this is actually only just part of a larger supercluster, which is a very large structure, but still fairly insignificant in the grand scheme of things. We think that from our position, we should be able to observe some 10 million of these. And in fact, this next slide is a map from the Sloan Digital Sky Survey. So in this map, we're standing at the center. And what this telescope has done is to survey the sky, much like a lighthouse. Okay? If we're in the center, this telescope has recorded the positions of galaxies in every direction, turning around like this. Okay? And each dot is a galaxy. The red parts are areas with more galaxies. And this is only a fraction of the total amount of galaxies that they measured, that they detected. But it already contains like millions and millions of galaxies, right? And some of the ones furthest away, so the ones along the rim, their light was emitted 2 billion years ago. But this is not even the state-of-the-art galaxy survey. Like in the next few years, in the next 10 years, we expect to complete this map out to a distance of 10 billion light years. Sorry. So this is already getting quite close. The scenes we're seeing are getting quite close to the beginning, right? We said the universe was 13.8 billion years old, and we're seeing things that were happening 10 billion years ago now. So actually, I said earlier that the universe is infinite, right? But there is an edge that it makes sense to talk about. It's that defined by the position, the furthest away position from which light emitted at the beginning and traveling towards us in a straight line would be reaching us today. That defines the observable universe. There's obviously more universe beyond that. We simply haven't had enough time for light coming from those locations to reach us. But fortunately, as we allow more time, we're allowing more time for light and information from those places to arrive from. Okay? But let's look at the very early moments of the universe. So let's see what was going on then. Fortunately, we have very powerful telescopes that let us reveal this picture, which is probably the most boring one we've looked at the whole evening, right? This is what the universe looked like. Only in that calendar that I was talking about, this is only 15 minutes into January 1st. And it's a pretty boring picture, right? It's because the universe was pretty boring back then. It was just this soup of light that was everywhere the same. You know? But for every 10,000 places that you went to, only one would be slightly different. Only in that one place would you find a lump, a little bit more matter. And that's very important. So we point our very powerful telescopes and reveal this map of lumps in the early universe. And we've gone from the most boring slide to what I think is the prettiest one. So this is the very early universe. It's mapped by the Planck satellite. This is, you might have heard of the cosmic microwave background, but that's a fancy name for this. And what this means, what this is, are the tiny lumps from which everything evolved. Now, as the loss, with 13 billion years of time, the loss of physics transformed this into everything we know. Isn't that amazing? So you can actually put this into a computer and tell it to apply the laws of physics to it for 13 billion years. And you get very pretty pictures. This is a cosmological simulation that does precisely that. So it takes those initial lumps and tells you that, you know, those lumps will attract all the matter around it, and the clumps will start growing and growing and growing. And as things fall into them, they gain energy. Much like when you jump out of a plane, you start heading for the center of the earth very quickly, right? Well, the same thing here. And those infalling objects actually start colliding with other objects and heating up. And as they heat up, the first stars are born, and the first galaxies are born. And you'll see that happen here pretty quickly. You know, in the cosmic calendar that I was talking about, it's not until May that the Milky Way appears. And so yeah, that would be probably like galaxies forming and stuff. But you're gonna have to wait until September for the solar system to come around, for the Earth to form. And as we said earlier, it's not until 10:30 p.m. on December 31st that us humans appear in the picture. And we just should feel incredibly privileged to live at this time where we can use technology and our minds to learn about the universe that we live in, to try to answer the questions of where it is that we're coming from and why we're here. And I think these are beautiful questions that humanity should address at some point. And I think, and I'm pretty sure, that some of the people that will answer these questions are in the audience today. So if you find this interesting, and if you feel curiosity, keep that curiosity, ask questions, and believe in yourself, because you can be a great scientist as well. And you can ask me any questions as well if you want. So when this ends, which will be in a few seconds, we can go to the questions. Thank you very much. All right, I'm going to turn the lights on.